Okay, this video is about graphing irrational functions. I don't want it to be too terribly long, so I'm going to break it up into two videos. I don't know what's going on in that room. The first video is going to be maybe the first 3 steps of graphing a rational function, and the second video will be the last 4 through 7. So I think on the worksheet that you have, it doesn't have step 7, which it should have step 7 because you can't really graph it without plotting some extra points. So here we go. A rational function is a fractional function, so every one of these is a fraction function you can see. And so that means that there's some problems with the domain. There could be issues where you might divide by 0 potentially. So you first have to, the first step is to find the domain. So let me just make this statement. Whatever else happens with cancellations or whatnot, the domain is the domain forever and ever. That's what the domain is. So whatever else we do in simplifying this guy, that's the domain. All right, so number 1, how could we find the domain? We allow everything in except for division by 0. If you set the denominator equal to 0 and solve, that will tell you what you can't let in. So for instance, to find domain, we'd say x squared minus x minus 12 equals 0. We would solve this quadratic equation. This will be true. You could factor this into x squared minus, let's see, that's x squared minus x minus 12 into x minus 4 times x plus 3. When x is equal to 4 or when x is equal to negative 3, this will equal to 0. So when x is 4 or x is negative 3, this would be dividing by 0. So the domain of this is it can't be 4 and it can't be negative 3. You could also write that in interval notation if you wanted to. Interval notation would be this if you needed to write it like that, where you sort of hop over the values that are problematic. That would be the domain of that guy, number 1. The domain of number 2, you would set the denominator equal to 0. And find out where it would be a problem. This will also factor, this is difference of squares. And so the problems here is when x is negative 2 or when x is 2, so you can't let those guys in. In the interval notation, it would look like this. Number 3, where would you be dividing by 0 when x is negative 1? You'd set this equal to 0, x plus 1 equals 0 and solve. So x can't be negative 1. You could write that in interval notation like I did for the others. Where would the problem be here when x is negative 3? That would be the problem. Okay, so that's number 1. Find the domain. All right. So number 2 and number 3, they have to go together. I'm going to talk about number 3, and then we're going to go back and talk about number 2. Number 3 says find any vertical asymptote. So by default, a vertical asymptote comes from a place in the denominator where your function would equal 0, where it's undefined. So by default, x equals to 4 and x equals to negative 3. These are vertical lines. These places where it couldn't equal, these are vertical asymptotes. So I'm just going to write it like that. That's a vertical, this is the domain, okay, and this is the vertical asymptotes for this. What is a vertical asymptote? If you recall this function, which you're familiar with, maybe f of x is equal to 1 over x. This is known as the reciprocal function. It really looks sort of weird. This is what it looks like. This is what it looks like. Why does it look like this? Well, what is the domain of this? The domain of this is where where is any real value of x can go into this except for x equals to 0, because then it would be dividing by 0. So x is not allowed to be 0. Well, you notice that your function basically freaks out when it gets close to 0. It's like, no, I'm not allowed to do that. I'm not allowed to do that. And what does it do? It will either shoot up to positive infinity, like it's doing right here when it gets very, very close to 0, maybe at 0.05, 0.04, 0.02, 0.01, 0.0001, it's going to go to positive infinity. Or on this side, when it's negative 0.04, negative 0.03, negative 0.02, it's going to shoot down to negative infinity on this side. What's happening is when your graph approaches a vertical asymptote, it freaks out, and it will either go to positive infinity or negative infinity. And in this case, it does both of those things. It doesn't have to do both of those things. Right here, what you're seeing where it's hugging this horizontal line, this is a horizontal asymptote right here. A horizontal line that it approaches. So a vertical asymptote is the line that it approaches. And where does this come from? Where it's going to be dividing by 0. So we'll go through problem 1, 2, 3, and 4 and say what are the vertical asymptotes. So by default, values where it's undefined turn into vertical asymptotes. All right? X equals to negative 1 is a vertical asymptote. X equals to negative 3 is a vertical asymptote. This is a place where the function is undefined and where it will do this sort of behavior. Unless there is a hole. How in the world do we find holes? Well, holes come from cancellations where you have common terms in the numerator and denominator. So then your function doesn't totally freak out totally going to positive and negative infinity. It just is undefined with the open circle right there. So let's look at what happens here. How do you find them? You factor the numerator if you can. So let's factor the numerator. It is factored. Factor the denominator. We already did that. We can rewrite this into x minus 4 times x plus 3. And this was originally x squared minus x minus 12. I might want to look at that. So do I see a common factor here? No. That means these guys are full-on vertical asymptotes. Done. No holes. That's what we determined. No holes. We checked for it. Okay, right here. Factor the numerator. Okay, this is x times x minus 1, right? I can pull out an x squared. Down here, factor the denominator. Do you see any common factors? No, nothing in common. That means that these guys are still very much vertical asymptotes, and we check that there's no holes here. All right, up here, factor the numerator. This is x squared minus 5. This can't factor with whole numbers, so that's what I count as factoring. Technically speaking, you can factor any polynomial, but sometimes you have to use square roots or imaginary numbers. That's not the kind of factoring I'm talking about. Can we factor this with whole numbers? And we can't, so this one's done. So I mean, that means there's no common factors. So this is a vertical asymptote and there's no holes. So we checked for that. Okay, ready? Let's go down here. Factor the numerator, okay? This is gonna factor into x plus 3 times x minus 3, because that's difference of squares over x plus 3. Do we see any common factors? We do. And so what happens here is x plus 3 and x plus 3 cancel. Now the domain has not changed. Still x is not allowed to equal to negative 3. But what happens is if you have a cancellation like this, then this value, x equals to negative 3, gets a new name. It is no longer a vertical asymptote. It is known as a hole. And it turns out that was our vertical asymptote and it went away. So now there's no vertical asymptotes. Just as a for instance, what if you had some function like this, r of x is equal to x plus 3 times x over x plus 3 times x minus 3. Let's suppose we had something like that. Okay, then we'd say, oh, what are our vertical asymptotes? X is negative 3, x is positive 3. These are vertical asymptotes. But then we factor the numerator and say, oh, is there a cancellation? There is. So that means that x equals to negative 3, which is where this came through. This one gets a new name called a hole. And x equals to 3, which is what this one came from. And this is when we set it equal to 0 and solve, right? When would x plus 3 equal 0 when x is negative 3? That's what I'm talking about right here. Maybe I'll use a different number so it's better. Let's put 4. X minus 4. Then x equals to 4 would be a vertical asymptote, and x equals to negative 3 would get a new name called a hole. So we did 1, 2, and 3. So let's go ahead and find the y-intercept while we're at it, and then we'll do the rest. So I'm kind of skipping around here. We did 1, we did 2, we did 3. Let's go ahead and do 5. Find the y-intercept. How you find the y-intercept is you let x be 0 and solve for y. So y-intercept. This is what I wanted to make sure I don't erase. Let me see. We got the domain, okay. The vertical asymptotes and no holes. Y-intercept. We are going to let r of 0. We're going to find what r of 0 is. So that would be 0 minus 5, or negative 5, divided by 0 minus 4, negative 4, times 0 plus 3, positive 3, or negative 5 over negative 12. So we find the y-intercept is going to be 0. A negative over a negative is a positive, 5 over 12. All right, that's what we got so far. What is the y-intercept? Okay, well, we'll say what is r of 0? All right, 0 squared minus 0 over 0 squared minus 4 gives us 0 minus 0, 0 minus 4. Negative 4 goes into 0 0 times. So the y-intercept here, when x is 0, y is 0. All right, the y-intercept here, find out what r of 0 is. That's going to be 0 squared minus 5 over 0 plus 1. 0 squared minus 5 is negative 5. 0 plus 1 is 1. The y-intercept here is going to be when x is 0, y is negative 5. All right, r of 0 here, let's see what would that be. R of 0 would be 0 squared minus 9 over 0 plus 3. 0 minus 9 is negative 9. 0 plus 3 is 3. We get negative 3. So the y-intercept here, when x is 0, y is negative 3. Okay, that's it for this first portion of the video because it's just going to be too long. Second half, we're going to tackle, so we did 5. Second half, we're going to tackle horizontal asymptotes and maybe finding the x-intercepts if it's convenient. If it's not, we'll skip that part. And then 7, plotting important points. All right, see you in a sec.